whether you have done both survey or not, right? I give you 10 minutes so that we will start our class at 10 minutes past 12, right? So please answer the SSRT and also COS survey now. Okay. While waiting for others to answer the survey, I think we need to start our class now because it's already 11 minutes past 12. I will first start with the phase diagram part. Okay. So please pay attention to the video. All right. I will give you time. Maybe in the rest time, I will give you time to answer the question again lah, to answer the survey again. Right. So.
Bismillahirrahmanirrahim. Welcome back to my lecture on this one is phase diagram for metallic system. Right, we'll have a look at what phase diagrams are all about. But to mind you, right, phase diagram is very important for engineers. It's a very powerful tool that you must know that you will be using in your career later on. So let's listen up, what phase diagrams are all about. These are just your learning outcomes, right? You are expected to sketch simple isomorphous eutectic phase diagram and labeling the various important regions, the liquidus, the solidus, and the solvus line, right? And you notice that there are new terms that you have never seen before: isomorphous, eutectic. I'm not sure, maybe you have heard liquidus, solidus before. But of course, in this topic, many things are quite new to you, but it's interesting to learn, right? So what are you expected to be able to do is that given a binary phase diagram, binary means two component, binary means two, right? You should be able to tell what phases are present, what is the composition, and how much do we have of the phase. So mass fractions mean amount lah, right? All right, and then apart from those, you are also expected to be able to locate the temperature and composition of all eutectic, eutectoid, and peritectic phase transformation. Here again, you see new terms, right? They are sounding a bit different, a bit strange, and doesn't give you any sense. But after you discover about phase diagram, you know what they are, right? So we expect you to be able to even write the reactions for all these three types of phase transformation. What they are all about is about phase transformation. They are changing their phase, all right? Okay, and then one last thing that you will discover about the phase diagram is dealing with iron carbon. This is a very important system, very common system, right? Definitely you will be coming across iron carbon in your other courses and also in your career as an engineer. Okay, so when you are given this iron carbon phase diagram, you should be able to specify whether the alloy is hypoeutectoid or hypereutectoid. Notice we call alloy here because this is iron carbon. So this is an alloy. Okay, you must know that by now, right? And then there is what we call proeutectoid phase. So you should be able to know what is the proeutectoid phase, compute the mass fraction, make schematic diagram. So that are all the nutshell, in the nutshell, what you are expected to be able to do after we learn about phase diagram. All right, so sit tight. Let's listen up about this and let's look at our phase diagram. The first phase diagram I want to introduce to is the unary phase diagram. All right, this is nothing new, All right, I know you have learned about unary phase diagram looking like this. All right, what is it? What is the system? The system is water, H2O. You have seen this even in secondary school. All right, what is the axis? The axis is pressure versus temperature. What is constant? Okay, the constant is composition. So there are basically three variables. Composition is constant because here we are not varying the composition of the water. So that remains. Yeah? All right. So what do you have? You have like three separate regions. These regions of solid, region of liquid, region of vapor. Okay, separated by the three lines here. And you notice that, okay, there are like three different phases, as I mentioned: solid, liquid, vapor. They are all 100% vapor in itself, 100% liquid, 100% solid, no mixture. So this is a very simple system, unary. Okay, so it will tell you whether you're going to have ice, you're going to have water, or are you going to have steam, depending on your temperature and also depending on your pressure. That's all what phase diagram is telling you. Okay, these three different things, solid, liquid, vapor, this is what we call phase. Okay, so there are three phases for the system: solid, liquid, vapor. Now, this is simple. Okay, let's move on and see the other types of phase diagram. Now, this is what we have is sucrose water phase diagram. Now you have sucrose, maybe we can just call it sugar, okay, for simplicity. It's just a type of sugar here, sucrose and water. So you two components, you have sucrose and water, okay. And now you notice that my phase diagram is not pressure anymore. It is temperature versus composition. This is composition of what? Composition of sugar. This is what you add into the system. Okay, so because it has two components, we call it binary. Okay, now what do you have? This is only showing you from 0 to 100 degrees Celsius, from 0 sugar to 100% sugar. That means over here 100% sugar, pure sugar lah, nothing else. Okay, I have all sugar. Over here you got 0 sugar, but that means you have pure water, right? Then you continue to add in the sugar, so you're gonna have solution. So this line is telling you the maximum solubility limit for your sugar. If you add just a little bit, at what temperature you are, 20 degrees, if you add on 0, 10, 20, you are still a liquid. You manage to dissolve the sugar in your liquid. So it's still one phase, a liquid. Okay. And then you add more, 40%, you're still a liquid. But then when you reach this point, all right, that is basically at 20 degrees Celsius, you reach your maximum limit of sugar solubility. You would now start to have liquid and solid, the undissolved solid. So what is this point? This is about 65%. Okay, 65% is the maximum sugar that you can dissolve at 20 degrees Celsius. After that, it's going to be a mixture. All right. So this is what phase diagram is telling you. Right. So below 65 degrees, if you're at 20, you're going to have liquid. If you are more than 65% sugar, at 20 degrees Celsius, you're going to have a mixture. As simple as that. So let's move on. Okay. Now look at this aluminum copper alloy. This is actually scanning electron microscopy, looking at the microstructure. So this is a very small scale. All right. So what you see is like two kind of regions. One is the lighter region at the back as the background, and you have this network going through the system. Okay. And this is aluminum copper. Okay. Now you notice that actually the two different kind of pattern, right? They are called two different phases. The lighter region at the back, okay, or the lighter region is actually, okay, a beta phase. We call it beta. For simplicity, we just call it beta. Okay, the darker phase, okay, the one that's more looking very, protruding, is what we call alpha phase. Okay, however, okay, notice that, or just be aware that actually in the beta phase, what do you have? What elements do you have in beta? What is the composition of beta? Beta would consist of aluminium and copper, because that's what the system is all about, aluminium and copper. So you got aluminium and copper atoms at the back there in the lighter phase. How about the alpha, the darker one? What is the composition of the alpha? Still, it is containing alpha and copper. Maybe they don't have the same composition. They don't have the same amount of aluminium and copper in alpha and aluminium and copper in beta. But still, the composition consists of aluminium and copper. You don't run away from that because the entire system is about aluminium and copper. Right? So alpha and beta, we call them phases. Right? While aluminium and copper, we call them components. So when we see phases, we are actually calling them different phases because they have different physical and chemical properties, including mechanical properties. So beta and alpha will behave differently because the arrangement of atoms inside is actually different. Okay, and they can even have different crystal structure. Okay, although they are containing same composition, right? So try to differentiate between components and phases. So you must understand about phases. Okay, we are mostly dealing with solid phases, right? But then solid phases, there are many. Before, when you learn about ice, you know only one solid phase, ice. All right, but now when you learn about metals, alloys and all, you now discover that solid phase can be in various forms, different microstructure, different micro constituents. So we call it, sometimes we call it micro constituent. All right, so that's your alpha and beta. They are solid, both are solid, but they have different look, they have different microstructure, they behave differently, they have different physical and chemical and mechanical properties. Okay, that is okay. Now, again, we are dealing with this water sugar system. I think this is quite easy for you now. This is just about reading the phase diagram, understanding the phase diagram. Okay, so what if I move my point? Let's say initially I'm here at A, and at A I'm actually at 20 degrees Celsius with 70 weight % sugar. What am I? I am a two-phase system. I have solid sugar and I have liquid, right? Then I heat it up. I add on energy. I increase my temperature, and then until 100 degrees Celsius, right? 100 degrees Celsius. But of course, my composition remain because I'm only changing my temperature. I'm still 70 weight % sugar, but I am actually now in one phase. Okay, I'm all converted to one phase, all liquid. See, so that is the effect of increasing temperature. How about now, let's say I change my composition, I add more sugar, right? So I add more sugar from 70, I add until 90. Now, at 100 degrees Celsius, with 90% percent sugar, I am again in a mixture region. I am a two-phase system, liquid and solid. That's all about composition, about phase diagram. So there's nothing very difficult. It's just about reading the phase diagram. So it should be easy for you. Okay, let's discover the different types of phase diagram. Okay, I'm going to talk a bit about these two phase diagram. Okay, this one, notice the shape of the phase diagram. Okay, just now we have different types of shape, kan? So now this is yet a different shape. Now it extends from one end, these lines extend from 0% to 100%. And then it is another line also encapsulating it, extending from one end to the other end. Okay, that has a specific name to it. It has a specific behavior to it. There is a specific reason for it. Okay, why? Okay, let me just tell you that this is a copper and nickel binary phase diagram. Two systems. Okay, I mean not two systems, two components. Okay, copper and aluminum. Now, what do you have here? You have a region with 100% solid alpha. You have 100% liquid region. And then in between, you're going to have a mixture of alpha and liquid. That makes sense. You know, when you try to heat up alpha, there will be a region where you have both alpha and liquid before it gets to 100% liquid. So this is the region where you have a mixture of alpha and liquid. Okay, but the specific shape that I have here, okay, the two lines, what we call liquidus line. Liquidus line is the line here that separates the region between the mixture of liquid with liquid. All right, so this is 100% liquid and a mixture of solid and liquid. A line that separates between the 100% solid with a mixture of solid and liquid is called solidus line. So by its name lah, you can tell. Kalau solvers tu, that means it separates solid with solid lah. All right, so what's so peculiar about this is because copper and nickel, right, they have actually, if I refer to this, they have same crystal structure. They have almost similar electronegativity. They have similar radius. So they are the size of the atoms are similar. Because of that, remember from chapter 4, Hume rotary rule says that if you fulfill all this requirement, you're going to have very high mutual solubility in each other. What it means is that I can replace copper with nickel. I mean, initially I have pure copper and then I can start changing my copper atom with nickel atom and I can reach 100% solubility. So high mutual solubility, I can say this system can have 100% solubility in each other. So I can replace nickel with copper, I can replace copper and nickel, right? So they are totally miscible in all proportions. That is why you observe this kind of phase diagram. It seems that, okay, initially I got 100% copper here, 0% nickel, right? And then when I start to increase my nickel, this composition is nickel, increase more nickel, I'm okay. I can get 100% solid or I can get 100% liquid at any, depending on the temperature. They are totally miscible, okay? And then until to this point, I have 100% nickel, no more copper here, right? So at this point, 100% nickel, the melting temperature here, because this marks between the region of solid and liquid. Therefore, this is called the melting temperature for pure nickel. Over here, you're going to have like from solid terus tukar jadi liquid. So I have pure copper here, therefore this is the melting temperature of copper. So what is the melting temperature of 40% nickel and 60% copper? So I have to read sampailah I reach to this point, katalah ni straight line. So this is the melting temperature of 40% nickel, 60% copper. right? So you can read, because this is the liquidus line. Actually, they are all the melting temperature of your alloy depending on what composition of nickel you have. So notice dengan tak nampak pula when I have 40% nickel, what's another 60%? Copper lah. Alright, so that it's I assume that you can see that. Alright, so when I have 80% nickel, then I have 20% copper. Macam tu lah. Right? So this is a very peculiar phase diagram, and we call this isomorphous binary phase diagram. Only if you have this behavior, okay, where you have the lines in the across the board, across from 0 to 100% composition, right? Okay, and then on your right here, binary phase diagram. This is yet another type of phase diagram. All right. What is the peculiar thing about this phase diagram? It looks different, right? It looks different than this one. So basically what you have this one straight line. This is quite prominent. The straight line is quite prominent. And then you have this V shape on top. This is also prominent. The point here is prominent. We call it like a triple point there. Okay, we'll talk about that in a bit. And then you have this kind of curve on the right and on the left. So let's see what we have. Over here, it says we got 100% alpha. Okay lah, whatever alpha is. And then over here, we got 100% beta. So they are solid lah. Okay, alpha and beta. All right. So here is the region of solid alpha and beta. It's a mixture of two different solids. Okay. And over here, you got 100% alpha. So this is a region where you have only alpha solid. Okay, but as you add more component of beta, it seems that you cannot form alpha anymore lah. Okay, you're gonna have a mixture of solid plus you have a liquid alpha and beta. And on here you got beta. So beta is rich here. So this is beta rich. This is alpha rich. And over here you're gonna have solid beta mixed with liquid alpha and beta. Okay. This is totally liquid. Okay. Never mind. This one is quite general again. But the point here is important. This point is what we call eutectic. Okay. What does eutectic means? Eutectic means easily melted. That's what it means. Okay. Why that point is easily melted? Yes. Let's say you move from here. You have a composition exactly at that point. That composition, and then you heat it up. When you heat it up, you initially a solid. You are just solid alpha and beta. So the phases inside you is alpha and beta. Reaching to this point at this temperature, you're going to change the solid to 100% liquid just like that. You know, there's no transition between alpha, beta, and liquid. It's totally alpha and beta changing into alpha and beta changing into liquid. Okay, if you are in this region, you are alpha and beta, and then in this region you have a mixture. You have a mixture between alpha, beta, and liquid. You know, so and then before it changes to liquid. But here also you got a mixture. The solid beta and the liquid alpha and beta. Okay, so over here you got a mixture before you can get 100% liquid. Over here no, it's just like orang kata petik jari saja, and suddenly when you change your temperature, you're going to change your solid. Suddenly you get 100% liquid. So this is the point. All right, so a very interesting point actually. So this is what we call easily melted eutectic. You know, if you do solder, you know soldering kan? You use that solder tu lah. Okay, that alloy. So you just heat it up, okay, dengan solder gun, and suddenly this thing is just melt, right? So this is the use of this eutectic behavior, right? We can easily solder our PCB board or whatever, because when we just heat up your solder, it will just totally melt. You don't see any mixture of solid in that melt. So it's such beautiful, subhanallah. All right. We talk about that one. So I will stop here. I will continue in a bit on this binary phase diagram. We'll talk more detail about that later. All right. So thank you so much for listening, and I'll see you in a bit.
Okay, we have done part 1. All right, just want to check first on our, what we call this, maybe we take 5 so that we can see our COS, whether it is answered or not. Okay. All right. So far, 52 of you have submitted the survey for COS. 48 not responded, and 3 in progress. So please take the opportunity for these 5 minutes to those who have not responded, and to those in progress to complete the submission. Right. We will start again our next part at 12:40. Thank you.
Shaitanirrajim. Bismillahirrahmanirrahim. Here I am again. Okay. Assalamualaikum warahmatullahi wabarakatuh and good day to all. Let's continue talking about phase diagram. We are back to the binary phase diagram. So in particular, we have this copper nickel system. Remember, they are of the same electronegativity, same crystal structure, and also similar radius, okay, the atomic radius. So they are 100% miscible in each other. They can dissolve in each other 200%, okay. And knowing this is a binary system, you have two components only, copper and nickel, and this is how it looks like. Okay, you have two phases, liquid and solid alpha. Okay, and alpha is said to be FCC solid solution. All right, so now the question is, we want to know the number and types of phases that are present. So it's not very difficult. Let's move that. Okay. Rule number 1 says, if we know the temperature, okay, we know the temperature, we know the composition. So C0 is always the point of interest lah. C0, composition of interest. Then we know the number and types of phases present. Of course, okay, you know two variables need fixed, then you can spot your location on the phase diagram. So it's important to locate your place on the phase diagram. So for example, let's say you are at 1100 degrees Celsius and your composition is 68% in nickel, 40% copper. If I want to trick you, I will say I am a 40% copper. Where am I? Okay, so if I say, okay, I can say 68% nickel, or I can say I am a 48% copper. So they are the same thing lah, because it's the whole system kan, the nickel and copper. So you be careful what you have. Okay, if I quote it in terms of copper, then you need to like see what is the axis. Is it in copper or is it in nickel? So be aware. So if I am a 60% nickel, here I am. Okay, 40% copper, 1100 degrees Celsius. What am I? What phase do I have at this point? I am a totally solid alpha, right? So I am only one phase alpha. If I'm here, I'm in this point B here. What is B? B is 1250. 1250. My composition is 35% nickel. I would be a mixture of liquid and alpha. So it's not difficult dealing with phase diagram. All the answers are in the phase diagram, but I'm sure you're going to have issues with phase diagram because students always say that they don't understand, they don't see it, but you better listen carefully, right? So it's very, very important to understand about phase diagram. It's not difficult at all if you listen very well to the lecture, all right? Okay, and rule number 2. If you know T and C0, that means you define your point on the phase diagram. Then you also can tell the composition of each phase. All right. So let's take a point. Okay. Now, example, you are actually 35% nickel to begin with. Where are you? You are 35%. Here we are. Okay, the purple line is where we are. That is the composition of my system, of our system, is the alloy that we are given. All right, and now let's say the temperature is 1320. Where is 1320? Or you are high up here, 1320. What are you here, or what are we? We are totally liquid. Okay, you are only now you have liquid. Your C0 is actually Cl. C is concentration. Is the composition of liquid. What is your composition? I got no other composition. I have only one phase. Therefore, my composition is what the composition of the alloy is. 35% nickel. That means I have 65% copper. All right. And then at TD. Let's say you are at TD. Okay, at TD, what are you? You are actually just total solid. Only solid is present at that point. Okay, what is the composition of the solid? Again, you got nothing else to share with. You are still 35% of nickel. Okay, and what happened at ini mana 1190? 1190 rasanya ada macam silap je ni. At TD only solid, so ini kat bawah lah 1190 here. Now, if you are at 1250, 1250 is over here. B ya, ini dekat B bukan D. Ini B. Okay, TB. 1250, you are in this region here, right? That point. Now, what are you there? You are actually a mixture of alpha and beta. Now you have two phases present. Okay, you have alpha and beta. Now we need to ask you, what is the composition of the two phases? What is the composition of the liquid? What is the composition of the alpha solid? Okay, how do I do? What do? I draw a tie line. Listen, where you are, if you are in a region of two phases, you need to draw a tie line, just a straight line that extends from the point to the right until you reach a boundary, and then to the left until you reach the boundary with the next region. Okay, so this is what we call a tie line. So once you reach to the right, this is the region with solid. Therefore, if I read the composition down here, this is actually the composition of the solid. 43 weight percent nickel is in the solid. I mean, the composition is of nickel. And on the left side, the line extends until to this point. If I read the composition at that point, this is 32 weight percent nickel, okay, in the liquid, because this is a region boundary with liquid. Therefore, that is the composition of the liquid. So we label it Cl, 32, C alpha, 43. So that's what the answer here, 32 weight percent nickel here, 43 weight percent nickel here in solid. So your solid and liquid, they have different amount of nickel inside. All right. So of course 32 nickel, the rest is 68% copper, and here 57% copper. That's what it means. So the amount of nickel in the liquid and in the solid differs. Okay, so how do you read? Again, you draw a tie line until you reach the boundary, okay, to the right and to the left, where it intercepts the liquidus line. That's what your composition of your liquid. Where it intercepts the solidus line, that's the composition of your solid. Simple as that. All right, just by drawing a line, you will read the composition of the phase, okay, each of the phase. Now, another question. How about the amount of each phase? Okay, so back to our point A just now. Over here, you are only a liquid, so you have 100% liquid, so no issue. Okay, 100% liquid, no solid, right? And then how about at point D? You are 100% alpha, so nothing else. Your weight percent is 100% in solid. The issue now is when you have two phases. All right, when you have two phases like at point B, how do you calculate the amount? Easy, very easy if you listen to me now. Okay, we are dealing with the tie line. You must have your tie line must be indicated where you are here. All right, so draw a line to your right until you reach the boundary with the other phase. This is the solidus line. Stop. That is how long your line is. And then you extend to the left until you reach the boundary with the next region. So stop. Okay, you label your line, or I will normally bring out the line. This is my line. Okay, I label it in this way. So on the left, that would be Cl, composition of the liquid. This is composition of the solid, and I am here. This is my C0. Okay, they label it as R over here and then S over here. That is just the distance, the length of the line here and here. Now, if you want, listen, if you want to find how much liquid you have, liquid is on this side. Okay, liquid is on this. If you want to know how much, you take the distance on the opposite side. That is the distance length S. So S over the total length of your tie line, R plus S. So that's what I have here, S over the total tie length. So what is S? S is actually C alpha. C alpha is 43 minus C naught. C naught is 35. So I have 43 minus 35 over the total length. This is 43 minus, this is 35, and this is 32. So 43 minus 32, I got 73 weight% nickel. Must write that, yeah, nickel. Same thing for solid. If I know this is 73%, I already instantly know this is 27%. But I can calculate using the tie line again, right? Now, because I want to find the amount of solid is on the right side. Therefore, I have to take the distance on the opposite side. This distance now is 35 minus 32 divided by the total length. So now I have R over the total length, R plus S. So I will get 27% weight% of nickel. Sorry, this is about amount. Amount tak payahlah sebut nickel ni. Amount means amount lah. Ada 73% of liquid and 27% of alpha. Itu je maksudnya. Alright. So if I have 100% 100 gram of alloy, then you know 73% is liquid and 27 grams is solid and 73 grams is liquid kalau saya ada 100 gram. So this is amount. What we do here is what we call lever rule. Okay, ni dipanggilnya lever rule. So I already explained to you, okay, when you have that the tie line, how you're going to deal if it is a liquid, you want to find the amount of liquid, you need to go to the opposite side of the liquid. So this is the opposite side. Macam tu lah. So this one is just to derive, to show you about lever rule. So if you understand how to do that, the concept to, okay, you just use it, tak payah prove it. Okay. Alright, so that's what lever rule is about. Maybe if you like, okay, I can just explain it one more time. Yeah. Okay, how do we use lever rule? So lever rule is used when you want to find amount of the phase. Okay, so from wherever you are, you need to draw a line until you touches the boundary on the right and the left. Okay, and then this is how we draw it out lah. So this is where you are, C0, and then you label lah. On the left ni ada apa, liquid. So this is actually C liquid, yang ini C alpha. Okay, so if you want to find the amount of liquid is on this side, you go to the opposite side, you ambil S. So it will be S over the total length. That will be amount of liquid. If you want to find the amount of solid is on the right, you take the opposite side R. That will be R over R plus S. Itu sahaja. Okay? Okay, so in here it shows you the same system, copper nickel, but we are showing you in terms of the microstructure development. What actually happened at the micro level? Okay, so if you are moving from datang dari mana ya, katalah datang daripada A, start daripada A is liquid. Okay, so if it is a liquid, it doesn't have any grain boundaries, nothing. So this is liquid at that composition 35. You learned that already just now. Now, once you reduce your temperature, you're going to hit this point B. Okay, when you hit that point B, you're going to start to have solid coming up because you are entering this region of solid and liquid. So you start to have some particles of alpha. All right. So over here, what it says is that dia label lah. Liquid tu is what is the composition. The alpha is what composition. All right. So we know because this at this point, if we extend the line, okay, the tie line, it will get to this point 46. So this is 46% for alpha because this is the alpha side. Ni 46% nickel. Liquid is on the left side. Dia kata ni 35 lah, masih lagi 35 because you are touching at the boundary there kan. That's the composition of the two phases. Now if you reduce your temperature further, you are at C, of course you're going to build more solid. Your solid particles of alpha getting bigger now. Initially ni ada 6 ni, so this one should be 6 also getting bigger. Okay. Now, with this point, at this point, notice that the composition of the liquid and alpha is changing because you are here. So you draw your tie line. Now it's 43, and then the composition for the liquid is 32. So that's what they tulis kat sini lah, 32 and 43. Reduce your line further until you are at the boundary here where you are going to change into solid. Okay, the last liquid to form kat sini lah. Okay, you dah habis dah your liquid at this point where the composition of the solid is 36 and the composition of the liquid is 24% nickel. Okay, this is the last liquid that you will see. When what happened now, tengok lagi the bigger now, the particles of the alpha getting bigger and bigger, right? And then reduce further, and now of course at E point you're gonna have 100% solid. So you have green boundaries. No more liquid, no more green region. It's all blue now with green boundaries. Must show the green boundaries to indicate it is a solid. What is the composition? Is the 35% nickel. That's it. So you should be able to sketch this microstructure, give the composition, and also be able to give the amount of the phases present at any point of the phase diagram. All right. This is to show you actually when you grow the phase diagram, you grow the phase. Sorry, bukan grow the phase diagram. When you grow the phase, you change into solid. Okay. If you do it fast, the rate of cooling is fast, and compare that at using low slow cooling rate, the microstructure that form will be different. Okay, definitely this is engineering. This is memang you should know this lah. Okay, the rate has effect on the rate of cooling will have effect on the microstructure. So dekat in this fast rate of cooling, you have core structure. Over here you have equilibrium structure. So ni nampak very uniform. Okay, sebab you do slow cooling, you give everything time for them to move, for them to dissipate the energy and all. But over here, because you're doing it fast, there will be the center would first to solidify, and then the outer bit will be last to solidify. So it forms like a core like this. So yang ni tadi, the last alpha to solidify is less than 35%. The first to solidify is 46%. Where is it? We are referring to this point. Okay, the first solid will come up here, 46%. Okay, the last liquid would be 24%. 20%, 24%, ataupun the last solid would be of course 55% lah kan, sebab itu yang you punya composition. So that's how the difference in the microstructure when you do fast cooling and slow cooling. Alright, of course we always relate microstructure to property. So you can see here where the tensile strength and ductility is influenced by the composition of your alloy. Okay, the more alloy you add in, okay, the more composition of the element that you add in, your tensile strength increases, okay, to a point, okay, and then it starts to reduce again. Okay, because you're gonna get more nickel at this point, so then it comes down. Normally, ductility would be the opposite trend with tensile strength. If it is so strong, then it's not ductile. Okay, so elongation would be on the opposite side. As you add more elements into it, the percent elongation will reduce, and then when you have more nickel, again, the behavior is actually now is increasing again. All right, so that is the influence of nickel ataupun influence of alloying on mechanical properties. Okay, I will stop there. We will continue this in a separate video. Thank you so much. Okay, I'll come back to you in the next video. Assalamualaikum.
Okay, Waalaikumsalam warahmatullahi wabarakatuh. We are going to go for another video, but before that, I think we take also 5-minute breaks where we'll start again at 9 minutes past 1, right? Maybe Dr. Putri have a question there. How do you find the topic and interesting, easy? So maybe you can answer it in the public chat, or you can answer it through audio, through the audio. Okay, I just checked the COS survey results. So in total, there are 2 people in progress, 41 not responded yet, and 60 have submitted. So those for the 43 students, please do it as soon as possible before we start our next video. All right. For the SSRT, I think for my part, as far as I'm concerned, maybe Dr. Putri will check on her part. All right. For my part, there are few lectures. All right. I think. 22 students answering for the C1 L1, all right, and then okay, 59 students answering for C1 L2, and then no student answering for C1 L3. Okay. We'll check for C2. Thirty-nine students answering for C2 L1. Okay. Twenty-nine students answering for C2 L2. And no student answering for C2 L3. So I believe some of you haven't yet completed the SSRT and COS, as I mentioned just now. COS is 41 have been answered by, and then the rest yet, sorry, 43 have yet to be answered the survey because 2 of you is yet to be completed. So I hope please do it by as soon as possible by today. And then about the things that mentioned by Dr. Putri just now in the public chat, that we are going to have exam 2 next Tuesday, which will cover from chapter 5 to chapter 9. And then one more thing, so the announcement will be made in ULEN. And then we will also have the distribution, change in coursework distribution, where the assignment will be 5%, quiz will be 5%, project will be 20%, exams will be 30%, and extended assignment will be 40%. This will also be shared in the ULEN, all right? Okay, I think now it's 10 minutes past 1, so we have to continue with part 3. Okay, I hope everyone please pay attention. All right.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Thank you for joining me again. We continue our phase diagram discussion, and now we are dealing with the binary eutectic system. So you should know now what is meant by binary. That means I have a 2-component system, and then eutectic is when I have a point where it is easily melted. All right, so that is the point where you have a sudden change. I shouldn't say sudden because all these are at equilibrium, but the change in the phase is like from 100% solid into 100% liquid without going through a transition, a mixture between solid and liquid. So that's what it means by eutectic. All right, so this is what eutectic, a special composition with a minimum melting temperature. So that's what it says here. So that is the eutectic composition, and this is the eutectic temperature. Very specific point. Okay, so you must be aware about that one. Now we are looking at another system, not copper and nickel, but copper and argentum. I call it argentum because it's Ag argentum. So in other words, this is silver. Okay, so I normally easily call it argentum. Okay, so there's no more isomorphous here. Okay, copper nickel, you remember isomorphous phase diagram looking like one line extend from one side to the other side. So this is isomorphous, copper and nickel. Ya Allah, kenapa dia meloncat? Sepatah balik sekejap. Alright, and this is nickel. But now it's looking eutectic like this. So this is very orang kata full of stories nah, because there's so many different phase region. I have alpha and beta in one place here, in one region. This is solid, alpha and beta. Although they are both solid, they are different phases because they have different properties. And then here we got a single phase region, alpha alone, a solid. Over here we got beta alone, solid. Here we got liquid, totally liquid, no mixture. However, in this region, you notice it is between alpha and liquid. Therefore, I have alpha and liquid here. Over here, it is between liquid and beta. Therefore, I have liquid and beta here. Okay, so this is a specific system, therefore you have the specific values indicated in the diagram. So if you look at this point, 8 weight percent, this is weight percent of argentum, silver. Okay, this is temperature. So if it is 0 argentum, that means it's 100% copper. So imagine initially you start with 100% copper and then you start to add on silver. You add in silver into it or substitute silver into it. You can only do that up to 8% maximum, all right, before it actually turn into alpha and beta or liquid and alpha depending on the temperature. So alpha is actually a solid, okay. It is rich in copper. Okay, if you read the phase diagram correctly, alpha is rich, alpha is copper rich. Only a bit of argentum. But beta, on the other side, it is argentum rich. That means lots of argentum in beta. Okay, alpha contains lots of copper. So take note of that. All right. Now, so we have gone through the different regions. Okay. So this is what I mentioned here, mostly copper, mostly argentum for beta. So you know because it is on the right side and this is on the left side. Okay. The eutectic reaction, if I can write, is this. Liquid at the eutectic composition will transform, this is reversible transformation, into alpha containing the composition of eutectic, plus beta, the composition of beta is eutectic composition. So this is the eutectic transition or transformation at this point, right? So, sorry, lompat-lompat. Okay, so if you move at that line, go down, initially you are a liquid and then here you transform to alpha and beta. Alright, so alpha and beta will be the eutectic composition. Okay, so what is it? It is, I have to extend my line. So just below the eutectic transformation line, 779, then my tie line will extend from this side sampai that side. So 91.2% would be the composition of beta, 91.2%. Of argentum. Mesti tulis composition mesti ada element. And then alpha would be the composition. What is it? It will be 8%. That would be 8% argentum. By the tie line, I draw the tie line. All right. So what is the eutectic composition? Eutectic composition itself is 71.9% argentum. So if you can follow that, you are done. You are good, you know, for the eutectic composition, must be able to write this reaction well. Okay, so let's pick a point. Okay, you are actually 40 weight percent. This one again now a different system, plumbum and stannum. I normally call it by the name of the acronym plumbum and stannum. So this is basically lead and tin. So normally people call it lead and tin lah, tapi in layman's term. But I prefer to use the scientific acronym. So 40% stannum and 60% plumbum alloy at 150. Locate your point. Okay, with that composition of stannum 40%, you are here, and then your temperature is 150. This is where we are. That's the point of interest. Now you can draw your tie line until you find the boundary on the right, you stop. Until you find boundary on the left, you stop. So on the left, you are actually alpha on your boundary. On the right is the boundary with beta. So I know this is a composition pertaining to beta, and this is the composition pertaining to the alpha. C alpha, C beta. All right. And then, so we mark our line here, R and S, fine. And you are here, therefore you are actually alpha and beta. This is the phases that you start with. Okay, so the phases present, alpha and beta. Composition, tadi dah baca. So from here, this is 11% of stannum for alpha, and for beta is 99%. Ini anggaran je lah, because it's very close to the 100 already. So it would be 99% of beta. Relative amount, senang. You know, if I can bring out this tie line, this is alpha. Therefore, if I want to find the amount of alpha, I have to go to the opposite side. I will take S. So S over the total length. Now, what is S? S is actually 99 minus 40. So 99 minus 40, and the total length is 99 minus 11. That's the total length of R and S. Therefore, I can quickly get my amount of alpha as 67 weight percent. Okay, so without calculating beta, also I can tell already that beta would be 33 weight percent, because everything must be 100%. Okay. So, but if you want to find beta, beta is on this side. This is beta side. Therefore, you want to move to the opposite side of the lever rule, the tie line. You take R instead. So it's R over R plus S. What is R? The length of R is actually 40 minus 11. So 40 minus 11 divided by the total length of the tie line, 99 minus 11. That's what it is. I got 33 weight percent. Simple je kan? Easy, right? So you need to tell what phases are present. You need to tell the composition. You need to tell the amount of the phases present. Voila, that's it. That's system number 1. Oh, sorry. Okay, now let's go into system number 2. We are moving our point. Okay, now where are we? We are 40, 60, tak apa, but now temperature is changing. We are moving into this region now. This is the point of interest. What are you? Who are you? What are we? We are actually liquid and a solid alpha. So alpha and liquid. Okay, what is the composition of the phases that we have? You draw your tie line. Tie line now will stop here, because that's the point where you are, kan? Dah jumpa boundary, stop there. That would be the composition of the liquid, because this is the boundary with liquid. On the left, you stop here when you extend your tie line. This is the boundary with alpha. Therefore, if I read off the composition, that would be the composition for alpha. Right now, my tie line is pendek, okay, a lot shorter. I still label it R and S. Okay, this is where the point of interest, you are at 40% stannum. All right, so composition of alpha is 17. You can just read from the tie line here, and composition of the liquid is 40 weight 46% of stannum. Done. Okay, amount, easy, level rule. Okay, what do you want? You want the amount of alpha. Where is alpha? Alpha is on this side. Okay, the boundary is here. So don't go for this line R, go for the opposite line S. So you have S. What is S? S is 46 minus 40. 46 minus 40. What is the total length? 46 minus 17. 46 minus 17, you got 21%. Okay, alternatively, if you want to find the amount of liquid, where is liquid? Liquid is on the right side. So don't take the amount, the length of the tie line here, but you need to go to the opposite side. Take R. R is what? R is actually 40 minus 17. So 40 minus, dia tak tunjuk, 14 minus 17 divided by the total length, I got 79%. If you check your answer, you add these two, you should get 100. Betul lah, 21 and 79. So what do you have more? You have more liquid than you have solid in this region. So you see that if you are closer, your point is closer to liquid, right? Betul, your point is closer to liquid, therefore you have more liquid. You are so far from alpha, therefore you have less alpha. Makes sense. Alright. Okay, so that is system number 2. Kita ada banyak sistem ni. Alright, ini baru number 2. Okay, now kita tengok dia punya okay, microstructure pula. Okay, very interesting. We like to ask you about microstructure. We like to ask you to sketch the microstructure, and you always get it wrong. Alright, so listen up. So this is the first region dulu. Okay, the first region is where you have the very close lah, very low percentage of stannum. You are along this line, and you see you starting with liquid. Nothing is shown. Okay, it's only blank, and the composition is whatever the composition you start with, C0. Okay, and then once you get into this region, you start to have a mixture. You masuk je region ni, you're gonna have a mixture of alpha and liquid. So alpha timbul sekejap, keluar sikit alpha, and you must label, this is alpha and this is liquid. And then when you reduce the temperature further into this region, this is 100% alpha. Therefore, you totally now got green boundaries, and this is alpha. You label alpha. Okay, and then habislah. Okay, dah tak ada lagi. So result at extreme end, polycrystal of alpha green, only one solid phase. Okay, so ini sahaja yang you dapat. Because it is very close to the end. Dia hanya masuk 1 region, 2 region, 3 region. Okay, so I hope you are clear on the microstructure development there. Now in the second region pula, more complication here. Okay, you are moving from this point liquid, fine, you dah label dah you punya liquid tu, shouldn't have any green boundaries because this is liquid. Okay, so the composition is whatever you start with, C0. And then you reduce your temperature, you masuk in this region, you're gonna have liquid and solid. Show this is your liquid and this is your solid. Okay, solid alpha. And then you reduce the temperature, suddenly you become all alpha again. So there you go, your green boundaries and your alpha. Now, because you already like a solid over here, when you reduce your temperature and suddenly you masuk pula into the region of alpha and beta, what happened? You're gonna have beta precipitates coming out from your alpha. So you got this red thing lah to show that these are the beta. That's how it happens. Okay. So this is the microstructure development at this point. Okay, so dekat sini apa dia cakap? Solid limit at T room, and this is solid limit at TE. Okay, tak apalah at this point tak ada ni. Ini solid ialah maknanya how much you can have stannum into your system at TE. This is 18.3. Okay, alright. So that is your second system. Okay. I already talked about this one lah. Initially liquid and alpha, then alpha alone. Okay, finally 2 phases, alpha polycrystal and fine beta phase inclusion. Dia panggil inclusion. Dia panggil precipitates lah coming out from the from the alpha solid. Okay. So everything is just making sense, logical, depending on where you are, you know, as you go down, what region. So tak ada apa, there's no Pandora's box ke apa kat sini. Is everything what you see in the phase diagram, that's what you get. So you just understand the phase diagram, itu sahaja. Now, this is where the important point is. This is our point 3, where your alloy composition is actually the eutectic composition. Okay. When you are at the eutectic composition, remember we have that reaction tadi. How do we write? With kata L, convert into alpha and beta. So actually this alpha and beta microstructure ni, how it appears is that it appears as lamella. Ni lah ditunjuk ni. Ini beta, ini alpha. So it happens to be alternating layers of alpha and beta. In reality, it looks like this. This is what we call eutectic microstructure. Eutectic microstructure. So you can see the alternating layers of alpha and beta. Sometimes they are fine, sometimes they are a bit coarse. Okay, so it depends on certain things. Now, remember beta, I said to you just now, beta is rich in stannum. So you're going to have lots of stannum trying to move into beta. So ni yang ditunjuk ni, all the stannum is moving into beta, and then your plumbum will move into alpha, because alpha is rich in lead. Okay, so you have diffusion going on here, right? All the atoms of plumbum trying to move into A layer, alpha layer, and then the stannum tin trying to move into the beta layer. So you can imagine they cannot run far lah. Therefore, they just run to the top layer, to the bottom layer. So that's why they grow into alternating layers. Okay, so they don't have to travel from bottom to up. Okay, so they just associate themselves, agglomerate or arrange themselves to be at the closest vicinity. So banyak-banyak plumbum will cause to have alpha, and banyak-banyak beta will banyak-banyak stannum will form beta line. So they become alternating layers. Okay, so they grow in this direction lah. Dia kata you just move along. So that's what happened actually at the eutectic point. Okay. So when we say eutectic microstructure, you must imagine it is happening like in these alternating layers. You must label which layer is alpha and which layer is beta. And alpha is on this side. What is the composition? It would be 18.3 towards this end. So dia kata 18.38% stannum is in alpha. That means it is rich in plumbum. Beta is rich in stannum, 97.8%. So how do they read this value? Because of the tie line, they extend it to the right, and then they read 97.8. So if you start with a totally liquid, and then after you cross the eutectic punya temperature, 183 for this system, suddenly your liquid change everything. And I shouldn't use the word sudden. Then it will change, liquid will change into alternating layers. So that's what you're going to see. You need to draw this eutectic microstructure. Beautiful. All right. Then system number 4. System number 4, where you have your composition of your alloy, dia kata between 18.3 and 61.9. So on this side lah. Okay, tadi kita macam cross kat sini, right? But now it's just in this region sahaja, between these two region. Okay, you start with a liquid. That's it. That's your liquid. That's the composition. And then you start to touch this boundary where you're going to have a mixture of alpha and liquid. You have your nucleus for alpha, particles coming out, alpha solid, all right? And then when you go near to the eutectic line, you're going to grow all your alpha, patutnya nampak besar lah, all this alpha become bigger. Okay, Okay, and then once you remember, just cross, before you cross the TE line, the eutectic temperature, okay, although the eutectic reaction happen here, they actually apply to all the temperature. Once you cross the temperature of the eutectic, whatever liquid that you have will turn into eutectic. So if I can say here, okay, eutectic ni, whatever yang alternating ni, hanya akan terbentuk if you change liquid into this lah. Okay, only liquid will change into eutectic. You cannot change alpha jadi eutectic, tak boleh. It's only liquid. So that's why when you see here, you have some liquid left before you cross. Dekat sini kan masih ada liquid before you cross the TE. Therefore, once you cross the TE, the already formed alpha before TE is still remaining. Okay, these four are still remaining. Tapi the green region ni, yang liquid ni, the liquid tu yang will change into eutectic. So that's why you have this kind of microstructure whereby you maintain the alpha that has formed before eutectic temperature. Okay, so this alpha is what we call pro-eutectic alpha because it's formed before crossing the eutectic temperature. All right, and when the liquid that you have before crossing the eutectic temperature, all that liquid will change into alternating layers. So inside the alternating layers, you still have alpha and beta. So we call that eutectic alpha, eutectic beta. Tapi this one we can call it pro-eutectic alpha or we can call it primary alpha. Primary means it comes first lah. Okay, so that's how it happened when you have liquid and then you change it into you cross the eutectic temperature, change it into eutectic microstructure. So I know that this alternating layers is coming from the liquid remaining before you cross the eutectic temperature. So all these are just telling you about the composition which you read by the tie line. If you are before the TE, TE ni adalah eutectic temperature. Before that, your tie line is shorter, nampak sampai kat sini sahaja. That will tell you the composition of the liquid and the composition of the alpha. Once you cross the eutectic temperature downwards, you go downwards, your tie line becomes panjang lagi. This one is the composition of the alpha and then this is the composition of the beta. So if you understand the basics, the fundamentals, then the rest is just a breeze. Okay, you would be able to calculate whatever, okay, wherever you are at the phase diagram. So this is what it is, reading the composition by the tie line and then calculating the amount depending on the R and S. Okay, this is the difference between above TE dengan below TE lah, because your tie lines will be different. So it will give you the amount of alpha and beta. Over here will give you amount of alpha and liquid. But the alpha that you calculate here would be referring to the primary alpha or the pro-eutectic alpha. That is the amount of this, right? But the alpha that you got here would be a combination of the eutectic and primary. So itulah dia punya complexity-nya. Alright, so alpha here, although we just say alpha, tapi you remember part of the alpha is the primary alpha from here, and then part of the alpha will be sitting in the alternating layer, which is the eutectic bed. But the beta is everything inside the laminating lamella. Okay, the laminating apa panggil alternating layers. Wonderful. Alright. Yeah, you need time to digest, okay? But never mind, just listen to me first so that it will be easier for you. So, you know this is the point of eutectic, okay? Any composition that is less than that, we call it hypoeutectic. Any composition more than that is called hypereutectic. Mudah saja, nothing difficult. Okay, how about the microstructure? So if it is eutectic, you see you have a complete eutectic microstructure, right? But if you are hypoeutectic composition, you have your primary alpha. We have seen that before, kan? Sebelum ni, slide sebelum ni. This is the primary alpha that were formed before you cross the eutectic temperature. And for hypereutectic, instead of alpha, you're going to have beta because you will be in this region. Okay, there's no alpha in this region, is beta. So your primary macro constituent would be beta. Kat sini alpha. Itu saja beza. So they appear the same je. Dia yang ini adalah particles, round particles. The rest is the alternating layers. Right? Wonderful. That's where we're going to stop because we're going to move into a new phase diagram. So I will stop there and I'll see you in a bit. All right. Thank you so much.
Okay, Alhamdulillah, we have already covered part 3. So we are going to proceed directly to part 4 because we are running out of time. I will share with you the part 4 immediately now.
Bismillahirrahmanirrahim. A'udzubillahiminasyaitonirrajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Okay, we are back. We have, I think, the last bit about phase diagram. We have been talking about isomorphous and binary eutectic phase diagram. We have seen copper nickel, we have seen copper argentum, plumbenstanum, and we have talked about microstructure development, right? So I hope those knowledge are already settled in. Hopefully we can continue on, and all those fundamentals would be just useful for continue on with this another diagram looking more complicated, looking more complex, all right, and it still have that eutectic feature in it, but we're going to extend our notion about eutectic, okay, to eutectoid. So how do they differ? Basically, this is about iron-carbon phase diagram. As I said before, iron-carbon is a very important system because this is actually steel. Iron-carbon is about steel, and you know that we use steel a lot in our daily life, in industry, you know, in all applications, it's all using steel. So we need to understand steel well. And as engineers, you have to know about their phase diagram. Once you know their phase diagram, you know the phases present, the microstructure, and about their properties. So it is very, very important to understand this. So there are two important points of the iron-carbon phase diagram. One point is over here. This is what we call the eutectic point. Okay, what is eutectic? If we remember from our plumbum argentum system, eutectic is when you have liquid convert into solid, okay, at one particular, the lowest temperature, all right, the lowest possible temperature. And we have conversion of liquid, 100% liquid, into two solids, right? So liquid changing into two different solids. Over here we have gamma and cementite. Fe3C is called cementite. This is particular to iron carbon lah, ya. Cementite, or sometimes we call it carbide. So if you heard that name, it's the same thing. Okay, cementite or carbide is Fe3C. So you have eutectic reaction, conversion from liquid into gamma and cementite. That's called eutectic. Eutectic is peculiar to liquid lah ya, memang conversion of the liquid. If you have a conversion of solid, now I have gamma changing into two different types of solid. Okay, these are two different phases of solid. I have alpha and also cementite. So all these are solids. So transformation from one solid into two different solids is called eutectoid. Where do you find eutectoid in the phase diagram? Let's find where that point is. All right, so actually the point of conversion of gamma into alpha and cementite is this point. Okay, it is signified by a straight line. Okay, and then you have a V curve. That's what I mentioned before kan. Kat sini pun there's one straight line and a V curve. So that's your triple point, very important point because all the phases surrounding that region, they are in equilibrium. So I would have liquid, I have cementite, I have gamma coming to equilibrium all at one point. Over here I have austenite and I have alpha and cementite coming to equilibrium at this point. So eutectoid point here and eutectic point are important. You should be able to write this transformation, okay, reaction, and also this one. Okay, again, if you want to know the composition of each of these phase, of course you need to draw the tie line just below the line. Of course, this temperature for it, this is what we call eutectic temperature, and this 727 is called eutectoid temperature. For the iron carbon phase diagram, eutectoid transformation is more important, all right, compared to eutectic. We are working in the solid region lah. That's why we are focusing on eutectoid. Eutectic we have dealt with Plumber and Gentum. Now we're going to talk more about eutectoid. Okay, so again, what is the microstructure for eutectoid? So you can still see here, if you are here, you are 100% austenite, and that is signified by the green boundaries, all are austenite. But now your austenite, only austenite, okay, will change into alternating layers because it has passed through the eutectoid temperature. So austenite will convert into cementite and alpha alternating layers. So the background, the blue or green color, whatever you see, is actually alpha. This is the softer bit of the microstructure. It's called ferrite, alpha ferrite. And the red one is actually what we refer to cementite, and this is very hard microstructure. All right, so this is how it's looking like for eutectoid. Similar to eutectic microstructure, kan? Very similar, alternating layers, konsep dia semua sama, except that it is conversion from solid gamma, austenite, we call it austenite, into alpha and cementite. So eutectic, before we learn is like conversion from liquid to alpha and beta, kan? But over here we have austenite and cementite. Okay, so if I have alternating layers of gamma and cementite, so this is eutectic lah, eutectic microstructure. If I have alternating alpha and cementite, then I have eutectoid. Itu you kena take note. Right? So basically, if you see at this phase diagram is more complex, so many lines everywhere. All right, so you have totally liquid here, you have delta here, the small region up here. In fact, there's one peritectic reaction above here, so never mind, we can escape that for a while. And then we have austenite. and then we have in this small region is alpha. Therefore, the region between alpha and austenite here is combination, a mixture of alpha and austenite. Over here is a region between alpha and liquid. Therefore, I have gamma and liquid. So I have gamma and liquid here. Over here, I have liquid, and also the boundary is with cementite. So I have liquid and cementite. All right, over here, what do I have? I have a boundary between gamma and also cementite. Therefore, I have cementite. And over down here, I have boundary between alpha and cementite. This is alpha and cementite. Okay, so it's always working that way. Okay, whatever it is sandwiched between, so that's what the mixture is consists of. And take note that this iron carbon phase diagram, it is temperature versus what is it versus? It's versus weight percent of carbon. And you see that the scale is only up to 6.7. We actually do not care about what happened after 6.7 because if you add too much carbon to iron, it's no use. It becomes brittle. So engineers, we are not bothered about what happened beyond that. So normally iron carbon phase diagram will stop at 6.7, but we know that the boundary here at 6.7 is actually boundary with cementite. So cementite is very tough, very hard. That's why, you know, if you put more, you're just going to grow cementite, you're going to have cementite, and it becomes very brittle. So that's in a nutshell about iron carbon phase diagram. Okay, so over here, okay, just now alpha and alpha and cementite. Okay, this eutectoid microstructure is also have a specific name, what we call pearlite. Okay, so pearlite, when we mention pearlite, is actually, you know, at the back of your mind, it is alternating layers of alpha and cementite. So instead of calling it eutectoid microstructure, we have a specific name, pearlite. Okay. Right. Over here, well, understanding about this iron carbon phase diagram actually is the same concept with the rest of the phase diagram. So it shouldn't be more difficult. It just look a bit complex. Itu sahajalah. It shouldn't be that complicated. All right. Now, if you are a hypoeutectoid, so mana hypoeutectoid? Eutectoid itself is here. Okay, that is the composition of eutectoid, about 0.76 weight percent of carbon. Kalau your composition is less than that, then you are hypo, okay, hypoeutectoid. So you may be along this line lah, all right? So let's look what happened to the microstructure development. Okay, so let's say you start from austenite gamma here. So this is the microstructure with grain boundaries because gamma is a solid. And then when you start to reach to this boundary, you remember that this region is between alpha and gamma. All right, so you're going to grow alpha once you reach to this point. So your alpha will grow out of the grain boundaries. In this case, it is like more prone to come out from the grain boundaries, because you know grain boundaries is a region of defect. Lots of empty space there, so it is of higher energy. You will probably grow new microstructure from there, so it will come out from the grain boundaries. Okay, the alpha will grow from the grain boundaries. As you go down the temperature, okay, you reach to the 727 line. Just before that, what happened is that you're gonna grow more alpha, because when you go down, then you're gonna convert into more alpha. So that alpha that you started along the grain boundary will grow like a river, right? So this now along the grain boundaries is actually alpha, right? Once you cross the 727 line, which is the eutectoid line, okay, eutectoid line. What happened? Remember, in eutectoid, gamma is changing into alternating layers. So whatever gamma you have left before crossing the eutectoid temperature will convert into alternating layers. right? So once you cross down here, then you can see your gamma now change to alternating layer, but your alpha that you have formed before eutectoid temperature will remain as that river flow, as I said just now. Okay, so the alpha that you formed before, this is what we call pro-eutectoid alpha. So ini dipanggil pro-eutectoid ferrite, or ferrite is alpha lah. Alright, that's what happened, similar to the eutectic case, but now the names change a little bit. Okay, okay, so the same way, if you want to read the composition, the amount, you need to draw the tie line. If you draw the tie line above the eutectoid temperature, that means you're going to find the composition for alpha and gamma. Okay, so above the eutectoid, it would be about alpha and gamma. Kalau below, you already transform into eutectoid tu, you're gonna have alpha and cementite. That's the border, alpha and cementite. Alright, so of course the tie line will have different values now, or longer. Okay, this one is only short, right? And in this one is very long, right? The composition of the cementite would be 6.7% carbon, and the composition of alpha will be towards the end here, which is about 0.02, very small value. Right, so you can read the composition based on the tie line. You can find how much alpha you form, how much cementite you form by the tie line. If you notice, you are here, you are closer to alpha, therefore you're gonna have more alpha compared to cementite. All right, that's the rule of thumb of it. Okay, this is hypoeutectoid. You can predict what happens if you are actually hypereutectoid. Hyper, that means you're going to fall between this region onwards up to 2.1 here. Okay, kalau you fall into this region, then you are a hypereutectoid. Ini dia hyper. Okay, so hyper will be in this region. Now pick a place, so this pick a line, and then start with gamma austenite. Sampai dekat sini, what you gonna grow? You're gonna grow some cementite, because now you are bordering with this cementite and gamma. So gamma is already there, tapi cementite will come out. Okay, so how does it come out? Come out along the green boundaries. So these are cementite. The red one here is cementite. As you go down further, you are reducing your temperature, the cementite will form more. So it will grow along the green boundaries, forming like a river flowing here. All right, the red one. And then now, you reach already almost to the eutectoid temperature. What happened there? What happened is that the gamma that remaining will convert into alternating layers, but the cementite that has already formed along the green boundaries will remain as such, because they are already there. They are not changing to anything else once you cross the eutectoid temperature. Only the gamma bit will change into alternating layers. So now I can call cementite as the pro-eutectoid cementite. All right, and then you're gonna have alpha and cementite in the alternating layers. Okay, so you have to differentiate the content of the pearlite. Remember, pearlite is apa? Pearlite is this. Pearlite is alpha and cementite, and I would have some cementite before crossing the eutectoid, which is the pro-eutectoid cementite, and I will have some cementite inside the pearlite. All right. So then, if you know what you have, you see that your tie line is actually different before crossing the eutectoid temperature and after crossing. Then you can actually find the right amount of things. If you are above the eutectoid, you will be finding the how much of gamma and cementite. You have gamma and cementite. If you are below the eutectoid, what do you have? Below the eutectoid, you're going to be bordering with alpha and cementite. Okay, this alpha, this cementite that you find on above the TE would be the pro eutectoid, but the cementite that you find using the level rule below the eutectoid point would be including pro plus eutectoid. Dia ada campur dua because you know it is embedded in there. So if you find this amount, you minus from this amount, you will find how much is actually eutectoid, pearlite eutectoid. Okay, pearlite punya cementite. Alright, so of course doing exercises and then you will find understanding lah. So this is one example dealing with iron carbide. Okay, let's try to move that. Alright, so what you have here, you have 0.4% carbon. Right, so 0.4 is about here. This is hypo. I tengok ni pun I already know this is actually hypoeutectoid. Kalau hypo, I know I'm gonna form proeutectoid alpha. Nampak dia dah sebut. Okay, alpha atau ferrite. Alright, so maybe you can go through this example. They are asking that if you have that 0.4 just below eutectoid, that means they are telling you that just be below the eutectoid and draw your tie line below lah. Kalau below, it will be extending from this end to this end. What are the borders with? Borders with alpha. Over here you have alpha and over here you have cementite. Okay. So dia kata determine composition of cementite and ferrite. Senang je lah. So that will be reading of this value which is normally 0.02 and over this side will be 6.7. So bam, dah jawab dah. Okay, 0.022 ini CO, cementite 6.7. Alright. Amount of carbide referring to cementite in grams that forms per 100 gram of steel. So you are still along this line, tapi dia nak tahu how much carbide you have. Okay, just below, just below. So you are about in this region, you are alpha and cementite. So you draw already your tie line. You want to know the amount of carbide. Carbide is on this side. So you have to take the opposite distance R. What is R? R is actually 0.02 dengan 0.4. So 0.4 minus 0.22 divided by the total length of the tie line from this end to that end, 6.7 to minus 0.022. You get 100 times 100 grams, you get 5.7 grams of cementite. So a lot more, alpha 94.3. Dia malas nak kira dah, dia ambil just the completion of this. Complementing 5.7, you got 94.3 grams of alpha. But it makes sense, you are much closer to alpha, then that means you are a lot in alpha. So that's one bit. The other one is amount of pearlite and proeutectoid. If you want to know about the pearlite and proeutectoid alpha, this is a bit more complex. Okay, so pearlite means whatever you grow from in the alternating layers lah. Okay, remember when you are hypo, although you have alpha and cementite, part of it is pro and part of it is pearlite. Okay, in the form of pearlite. So the amount of pearlite and proeutectoid alpha, okay, what's we need to find out. Amount of pearlite equals the amount of alpha just below eutectoid. So you must see that only gamma will change into pearlite. So kalau you want to know the amount of pearlite, then you are interested to go just above the eutectoid temperature, draw your timeline there. then it's the short one je lah, ya. So then you need to find the amount of gamma. If you can find the amount of gamma, that means that is the amount of the pure light you're gonna have, because only gamma will convert into pure light. Okay, so berapa yang kita ada ini composition, okay, C0, C alpha, C pure light, gamma 0.76. Where is it? So up there lah, dekat sini. Okay, so kalau dekat point level apa tie line, this is 0.76 composition with gamma, right? That's the composition of gamma. Alright, so how do you find the amount? So the amount tu dia tak tunjuk ke? There you go. Alright, let me move this. Alright, so if you want gamma, gamma is on top here on the right, so you take the opposite side. Yeah, opposite side would be 0.4 minus 0.4 minus 0.022 over the total length. Total length is only from here 0.76. Okay, 76 minus 0.02. So you will get 51.2 grams of pure light. So this is how much pure light you have. Okay, compared to the amount of alpha that you have. Okay, tadi saya kata apa, dia adalah campuran kan. Okay, so pro-eutectoid alpha that you have, pro-eutectoid alpha that you have, because this is hypo. So you take the amount of alpha that you have, 94.3, okay, minus 51.2, which belongs in the pure light, okay, and then the rest is actually pro-eutectoid alpha. Itu sahaja. Alright, so you get the answer there. It's a bit tricky, but if you think properly, okay, you know what you're talking about, then you will be able to find the values. Here we're just going to show you again, you know, the effect of alloying elements on the eutectoid temperature. Okay, so it depends on what element you add in that will change the eutectoid temperature accordingly. This is for the composition, how it changes by the amount of or the type of alloying elements that you add in. And yeah, alhamdulillah, we come to the end of the phase diagram. Okay, we realize that phase diagrams are useful tools to determine the number, types of phases, the amount of each phase, and the composition of each phase, given the T and the composition of the system. And we know also now, we see allowing, okay, allowing to produce a solid solution usually increases tensile strength, decreases ductility. And also binary eutectoids allow for a range of microstructure. You can see the, you know, how colorful they are, you know, how rich they are. Subhanallah, mashallah. Alright, so that's it about phase diagram. I hope you will be able to solve several problems, and please come back to us if you have any queries at all. Alright, okay, thank you so much. Thank you for listening. Assalamualaikum warahmatullahi wabarakatuh.
Okay, alhamdulillah, we have already covered phase diagram for the metallic system, all four parts in all the video, or 4 parts of the video. So is there any question? Because we are running out of time, now is 5 minutes after 2. So I hope that you can complete. Those who haven't yet to complete the SSRT and COS, please complete it. And if you have any question, I think now is already past 2. So I think you can ask the question in the WhatsApp, or you can email the question to us. So I think that's all for today. Thank you so much for your kind attention, and hope to see you next week during the exam 2. All right, thank you so much and have a nice weekend. Assalamualaikum warahmatullahi taala wabarakatuh.